Okay, this video is called membrane ion pumps. I have college students, medical students, they come up to me and they ask me, oh, could you please do a video about membrane ion pumps, just the ion pumps? That stuff is so confusing. And so yes, here it is, a video about membrane ion pumps. And my explanation of it is the best. There's nothing even close. Most, med school professors the first year, they stink, okay? They're like old guys, ready to be put out for pasture, no longer capable of doing anything useful. So they have them teach the medical students and they consider it a punishment, so they're not too enthusiastic. Well, I'm just doing this as a hobby, so it's fun for me. And the first thing I'm going to teach you is that your professors are total ignoramuses about hypertension. They're going to tell you it's idiopathic, which means the doctor's an idiot and the patient's pathetic, cause unknown, so they call it essential hypertension. We know the cause. Or they're going to give you other BS. Oh, it's due to racism and socioeconomic disparity. That's all BS. It's a lie. Look, here's these people who are poor, running around barefoot in Africa and Kenya. 1,800 consecutive admissions to the hospital, adult men. This is in Lancet Journal, 1929. Author's name Donison. Blood pressure in the African native. This is where they eat a plant-based diet in Kenya. Out of 1,800, there was not a single patient that was hypertensive. They measured the average blood pressure of an African Kenyan man who was 60 years of age, let's say between, above and below, but averaging out at 60 years of age. Average blood pressure was 105/67. You heard that correctly, 105/67. There is no hypertension in plant-based communities except for super rare, really rare causes of hypertension, like a pheochromocytoma or something, a total zebra. You'll see that, I've been a doctor over 30 years. I've seen 2 of them, okay? And that's, being associated with 2 radiology departments, okay? Multiple radiology departments. It's super rare, super, super rare. Pheochromocytoma, everybody talks about it. Nobody ever sees one. All right, so now I'm going to show you, just a couple more. Here's the Papua New Guinea, where they used to eat 93% of their calories from sweet potatoes, which have only 1% of calories from fat. The lower the percentage of calories from fat, the less hypertension the population has, and the skinnier they are. So despite the fact they smoked like a bunch of chimneys, they had hardly any hypertension. So you want to know that, okay? You want to avoid hypertension, eat a vegan diet, okay? The low-fat vegan diet. And that also prevents coronary artery disease, okay? But nobody wants to do it, but that's what works. Okay, now here are the Tarahumara. They live in northern Mexico. They were split apart from another population called the Pima, which is essentially genetically identical to them. And they still eat their old-fashioned diet of corn and beans and squash and local greens and that sort of thing. Their diet is about 75% of the calories from carbohydrate, fat about 12% of the calories. I think they do eat a little bit of chia seeds. They have about, protein's about 13% of the calories. Yeah, people don't need much protein. Anyways, these guys can run over 100 miles in 2 days, okay? Every guy in town is fit. So I'm just letting you know this. This is what normal human nature is capable of. We're not designed to be fat, sick, and stupid. We're designed to be skinny and energetic and have tremendous endurance. Here's the Yanomami. These guys are a bunch of maniacs, live in South America and in Brazil on the border of the Venezuela, Amazon jungle. They run around, having little tribal battles where they steal each other tribes' women, okay? And spare me with that multiculturalism. They live like a bunch of savages, but at least they eat a plant-based diet, so they don't have hypertension. The average adult blood pressure was 95/61, okay? They don't add any salt to their food. When they check their urine, there's almost no salt. They don't have any hypertension, okay? All right, so now we're going to start getting into the ions, but I'm just letting you know that's how it works. One last thing before we do the ions. This is the external exogenous nitric oxide pathway. So nitric oxide, NO, is a vasodilator, okay? It's produced by your arterial lining cells, the endothelial cells, and it's a gas. Diffuses into the blood, into the lumina of the blood vessel, and prevents the platelets from clotting when it binds with them. It diffuses into the wall of the artery, into the vascular smooth muscle cells, and it inhibits them from contracting. So you need to know about that. When you eat plant nitrates, they come in as NO3, nitrate. Your tongue has bacteria that convert them to NO2, nitrite. They go into your stomach, and the stomach acid helps convert them to NO, nitric oxide, goes into your blood, you get systemic vasodilation. And that's why you don't want to use fluoride toothpaste, because it kills the bacteria on the back of your tongue. And then you will not undergo this conversion step and you'll lose the benefit of this as a way to help control your blood pressure. Okay, so this is the exogenous pathway of nitric oxide. You also get it, like I said, endogenously from it being made in your endothelial cells of your arteries. Okay, we're getting to the ions, and here we go. And the first thing we're going to talk about is how God made the earth, okay? The other thing is, I know your college, your med school, whatever, doesn't ever use the word God. That's right. It's based on atheism. Well, atheism stinks. It's incorrect scientifically and morally, and it leads to a healthcare system that just is designed to sell drugs. But I'm going to teach you how to really think of it. My ways are superior to the ways of your school, okay? So listen up and you get a chance to learn. This is God designing the earth, William Blake painting in 1824. Okay, so when he made the ocean, it was salt water. Okay, so that means sodium chloride. The thing you need to know is the salt water, the ocean, is like the extracellular space. He first made life in the ocean. Okay, and the extracellular space is seawater. So that means it's high in sodium. You have to know that. Salt water is high in sodium. You have to know that, okay? Salt water is high in sodium. Now, the next thing you have to know is that the water rinses over the rock. The rock is calcium carbonate limestone. And when the water rinses over the rock, it rinses calcium into the water, okay? So this is your extracellular space. It's high in salt, high in sodium, and it is high in calcium. You have to know that. That's the foundation of all physiology in the human body. So if you now have a cell and you want to create life, there has to be an osmotic balance between what's inside the cell and what's outside the cell. So in order to have anything inside the cell, which initially began as seawater, God had to pump out the calcium and he had to pump out the sodium, okay? So then he could put other stuff inside the cell. And what he decided to do was put potassium and magnesium inside the cell as the key counterbalancing ions. So think of potassium as the counterbalance to sodium, and think of magnesium as the counterbalance to the calcium that's outside the cell. So you'll have an osmotic balance, all right? Now we're going to talk a little bit about ions. First, one thing I want to say about natrium. So sodium is called natrium. That's the Latin word for sodium. And that's why the symbol for it is Na, for natrium. Kalium is like, it kind of reminds you, of course, of the plant kale, but that is the Latin word for potassium. So that's why K is the symbol for potassium, okay? Now here's approximate ionic concentrations. You have to know this. And it's very easy to remember that the extracellular concentration of sodium is very high because it's the same as seawater, okay? The extracellular concentration of calcium is high because the extracellular space is our physiological equivalent of seawater, so calcium will be high. On the other hand, it's the opposite situation inside the cell. Inside the cell in the cytoplasm, the potassium is high, okay? Whereas the sodium is low and the calcium is super low. So you have a concentration gradient between the extracellular space and the cytoplasm. And this is going to mean, ions want to equilibrate their gradient. So sodium wants to go into the cell. And the calcium also wants to enter the cell. And especially the sodium. I'll explain why sodium is such a crazy ion. Okay? Here now we have to talk about the plasma membrane sodium potassium ATP pump. So it brings in 2 potassium and it pumps out 3 sodium. So more positive charge is pumped out. 3 positive charges and 2 are brought in. So the net effect is it's making the outside of the cell more positive, the inside of the cell more negative. So the inside of the cell resting membrane potential is negative 65 millivolts. So I know there's some cells a little higher, a little lower, but for our purposes, the inside of the cell, let's say this is a neuron, is going to be negative 65 millivolts. Okay. Now, what's happening is you have this negative charge inside the cell, and that's going to make sodium want to come into the cell because its positive charge of the sodium itself is attracted to the negative charge inside the cell. So that's called an electrical gradient. The sodium is also attracted to come into the cell because the concentration of sodium inside the cell is low, compared to what it is outside the cell. Okay, it's like 10 times or more higher outside the cell. So sodium wants to come into the cell. All right, now you're going to have to pump other things out of the cell. You're also going to have to pump calcium out of the cell. And this is called secondary active transport. So using ATP, this is primary active transport, this pumping mechanism here to pump the sodium out. However, you can let the sodium come back into the cell, and this will run like a mill wheel. And when this spins, it will then pump out the calcium. So that's why it's called the knockout exchanger. Na for sodium, Ka for calcium exchanger, very often abbreviated NCX. So this is secondary active transport. Notice that the magnesium is drawn next to the ATP. I'll explain why in just a moment, but magnesium is the hero amongst the ions, the brave hero that controls the phosphates on ATP. That will make sense in just a moment. Okay, but you need to know that this sodium-potassium pump is the equivalent of an electrical battery. Okay, God designed all this stuff, and God is a billion times smarter than humans. Okay, and it's absolutely brilliant. Okay, because you have charge separation across a membrane barrier. Okay, and you have the flow of charge. In this case, a positive charge going outward is the net charge flow. That is an electrical battery. And the electrical battery produces energy that is used to run all these other pumps. So typically an average cell might use about 1/3 of its energy for this pump, whereas a neuron can use can use half to 2/3 of its energy to run this pump, which means this pump is very, 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 very important for a cell. Okay, and another thing to know is that inside the cell you have to maintain a constant osmolality. Okay, so the vast majority of positive ions inside a cell are the potassium and the sodium. That's about 98% of the positive ions inside the cell. So you don't want to eat a high salt diet because you'll gradually start accumulating sodium inside the cell, replacing potassium, and you will dissipate your ionic gradients. And that's a big part of why sodium causes hypertension. I'll explain that in more detail in the coming slides, but you need to know that. We're designed to eat tons of potassium, which is an intracellular ion that comes naturally from eating whole plant foods because the potassium is inside the cells and the plant foods as well. When you process a food, you scrunch it and grind it, and you then rinse it with solvents, and you rinse away your potassium. Then they add back sodium to make it taste better and as a preservative. So you end up with a processed food that's high in sodium, low in potassium. When you eat whole foods, you get the opposite. You get tons more potassium and hardly any sodium, and that's what you want. Okay, we're going to come back to that, but that ratio of potassium to sodium is called the K factor. Okay, now here's the part you've all been waiting for. Now we're going to explain how these ions really work and what you need to remember for them. Okay, here is calcium. Calcium is this lady, okay? And she is like a wife, an aristocrat wife. She is the big boss, matriarch of the family. Now the guy was thinking, before he got married, he would be the boss, but he found out that she's got his balls in her purse, okay? She decides when they make the two-back beast, okay? And if he pisses her off, she can file for divorce, and the system is designed to take away at least half of his money, kick him out of the house, okay? So she's the real boss, all right? She knows everybody. While he's working out all day, 12-hour shifts, she's on the phone, calling her sister and her mother and her other sister and spending his money, okay? That's just the way it works. So when calcium comes into the cell, it's the aristocratic mama matriarch who bosses everybody around. She is not reasonable. Whatever she says goes. There is no discussion, okay? That's how calcium works, okay? You need to know that. Calcium is mama, the aristocrat, who bosses everybody around. Now, here is the personality of potassium. Potassium is inside the cell trying to make everything functional. Potassium is working away at that sodium-potassium pump, Just like a manual labor, blue collar, middle class worker tries to make sure the trains are running, the trains are following their schedule, tries to make sure the construction of the streets is good so everybody can drive safely on nice, smooth roads. He's doing his job. He's making things work, okay? He's a responsible middle class that makes society a good, safe, healthy, productive society that's nice to live in, okay? That's potassium, the good guy, the middle class. The middle class man, like Papa, Daddy, okay? Daddy's doing the work, okay? All right, now I want you to meet magnesium. Magnesium has two things. You can remember magnesium is mellow. You can also remember magnesium is a hero. Magnesium is very strong and very brave. Adenosine ATP, adenosine triphosphate, has a very powerful phosphate bond that's released in reactions to power the reaction. Well, it's so powerful because it's got a big negative charge on it right next to another big negative charge. Now, how come it doesn't break apart? The reason it doesn't break apart is that magnesium is holding them together, just like magnesium holds these horses together. It is strong and heroic. That is magnesium. And so it doesn't allow this extra phosphate to be released until the time is correct in the reaction to release it. Okay, just like Charlton Heston in the movie 10 Commandments, it's got a tight grip on those horses. The phosphates are like the horses to make things run correctly. Okay, now here's the other thing magnesium does. Magnesium has two jobs, Okay, another job magnesium does, here you can see it guarding this ion channel. Magnesium will sit in the center of the calcium channel on your brain cells. This calcium channel is called the NMDA receptor, NMDA receptor. And the magnesium sits in the middle of it because it's attracted to the negative charge inside the cell. We talked about that, negative 65 millivolts. Okay, in your brain cells though, when glutamate comes across a synapse, it'll first bind to a sodium channel called the AMPA receptor, AMPA receptor, AMPA receptor. And sodium will initially come into the cell, and that will depolarize the cell, meaning that its charge will move closer to zero. And when negative 65 millivolt charge is depolarized towards negative 40 millivolt, now the magnesium doesn't have as strong of a negative charge to be attracted to, so the magnesium will pop out of the ion channel, and that will allow calcium to enter the cell. Okay, but this prevents overactivation of your brain cells. If a person is deficient in magnesium from their diet, then they're going to have less ability to block this receptor, and their brain cells are going to be hyper-excitable. So you will notice, if you've studied nutrition, that the paleo, keto, carnivore, low-carb diet people are basically a bunch of impulsive, lower level of human jerks who are rude and nasty because they can't control themselves. And that's because they don't get enough magnesium. Magnesium is located in the center of chlorophyll. Okay, so I'm just showing you that's one of the reasons why these meat and junk food eaters are so impulsive and bad behaved compared to us superior low-fat vegans who have clean arteries and highly functioning neurons. Okay. Now here is magnesium sitting in the center of chlorophyll. So when you eat the plants, you eat the chlorophyll, you get the magnesium. Another reason why you want to eat plants. As a general rule of thumb, all of the good stuff is in the plants. Lots of potassium in a whole food plant. It has to be whole food plant, not processed stuff. Whole food plant, you get the magnesium, you get the potassium, okay? You get the nitrates to make your nitric oxide, okay? You get the fiber to maintain your gut wall. You get the antioxidants, all the good stuff. Okay, now it's time to talk about sodium. What is the role of sodium in plasma membrane ion pumps? Sodium is the savage, angry poor. Sodium is the angry poor. Sodium wants to break into the city. They're pissed off that they don't get to be allowed into the city, okay? They're kind of like the untouchable, scumbag, lowlife, filth of the world, scum of the earth, okay? And they're outside the city, and they want to break into the city. So here they are, Victor Hugo's Les Miserables, trying to bust in. Okay, here they are. This was, a nice drawing of a fort, and they're busting across the wall. That's like your gut lining, or this is your cell membrane. and the sodium is trying to bust across the wall. Just remember that. Sodium is the angry pore trying to bust into the cell. Think of the cell being like a city. And the plasma membrane is to keep sodium out, unless you need to bring them in and pay them to do some cheap labor. That's what you're doing when you let them come in for a little while. But in general, you want to keep that sodium outside. They're the violent, low-life, angry, stupid pore. Okay? All right, so now here is a cell, and I'm going to show a little bit more what's happening, and several things are happening simultaneously. So when a cell is activated, you will have calcium entering the cell. When the calcium concentration in the cytoplasm is activated, that's like big boss matriarch mama comes in the room and she says, "What are you doing? Clean up your room. You do the dishes. You take the dog outside. You do this." Just bossing everybody around. So whatever that cell does, it has to do it when calcium levels rise in the cytoplasm. So if it's a neuron, the cell will release its neurotransmitter, which is most commonly glutamate. Glutamate is 90% of neurotransmitters. Is excitatory in your cerebral cortex. If it's a vascular smooth muscle, it'll make that cell contract. Cardiac muscle, it'll make that cell contract. Skeletal muscle, it'll make that cell contract. Okay, when insulin goes up in the pancreas, islet cells, they'll release insulin. Whatever that cell does, big mama, calcium, aristocrat, bossy, not reasonable, will make it happen. Okay. Now the cell, when it wants to turn itself off, it has to pump the calcium out. And we talked about how the most important way to pump calcium out of a cell is the NACA exchanger. It can pump like 2,000 calciums out in a second. It's incredibly fast. It's incredibly fast, okay? And you can tell God designed that. Okay, some regular biochemistry person, you want to tell them design a little ion pump that can pump out 2,000 calcium ions per second, they're going to tell you to go screw yourself, okay? They can't do that. God can do it easy, all right? Anyways, the NACA exchanger is a very fast way to pump out calcium. Notice that this sodium electrochemical gradient is used to pump calcium out. It's also used to bring amino acids into the cell. It's also used to pump protons out. Again, this is like an electrical battery of power that the cell uses. So you understand these ion pumps. Because you're pumping more positive charge out with the NAK ATPase, you will have a net negative charge inside the cell. Okay, negative 65 millivolts. You need to know that the inside of this cell is a negative charge. That's important to remember. Okay, now the ratio of potassium to sodium is called the K factor. In order to prevent hypertension, you need to have a K factor minimum of 5, preferably closer to 10 or higher, but at a minimum, at least 5 times more dietary intake of potassium than sodium. Okay? And here's just to give you a sense of some K factors. So with fruits, you got a K factor typically of about 100 to 500. So bananas have a K factor of 450 times more potassium than sodium. Okay? When you look at your starches, you're going to typically have a K factor in the ballpark of 20 to 60. Okay? So still great K factors. Veggies are more like in the ballpark of about 5 to 15. Okay? But that'll still prevent your hypertension. When you talk about just a pure meat like ground beef, you're talking about a K factor of about 4. Not good. That's like a mild hypertension. And then when you get into these processed food, they're a freaking disaster. Even the ones that pretend to be healthy, like Special K cereal, look at this K factor, 0.06, less than 1. Potato chips, less than 1. Cheetos, 0.14. That's a freaking disaster. That's like guaranteeing yourself hypertension. Okay, and I also want to tell you, the most important thing about this talk was that you understood the personality of those ions, because you're going to be dealing with ion pumps all the time in physiology, all right? And I remember back when I was a medical student, the hardest thing to remember was which ion is located where. Once you get my point about showing how God created life with seawater as the extracellular space, so it's going to be high seawater in sodium and in calcium rinsing over the limestone rocks, calcium carbonate, then you know forever, for the rest of your life, the extracellular space is always high in sodium and in calcium. And once you've got that, you know the counterbalancing ions are potassium and magnesium inside the cell. Magnesium is a 2+ charge counterbalanced to calcium, also 2+ charged. And the 1+ charge of potassium and sodium are the counterbalances to each other to maintain cell osmolality. Okay? You remember that, and you shall be golden. You shall be set for your entire rest of your career, and that'll tremendously help you to understand regular physiology, neurophysiology, cardiac physiology, skeletal muscle physiology. It will also help you to understand all the drugs. It'll help you to understand EKGs. It'll be very useful to you forever. Okay, and this was just a Sam Kinison comedy where he told people, about solving the problem of world hunger. He said, don't send food to people who live in the desert. He says, send them luggage. Okay, and that's what I'm going to tell you too. Spare me the BS about racism and socioeconomic disparity with hypertension. Bullshit. The reason why minorities and other people have a lot of hypertension is because they eat too much processed food and too much meat, okay? Eat your plants and veggies like your grandmother told you, and you won't have hypertension, okay? Communities that eat that way, they never got hypertension. Okay, now we're getting to extra credit because we talked all about calcium management in terms of how it comes into a cell and how it's pumped out of a cell. But there's a second, more advanced level of calcium physiology in terms of intracellular signaling. And I want to introduce you to some of these people. Okay, here is Big Mama, the aristocrat, the queen, the matriarch, the boss of the house. And here's the poor old man on his one day off. Mama is helping him because his glasses are broken, slipping off. And who is this lady who looks like she's about to spank his bottom, or more likely she's about to pilfer his wallet out of his back pocket? Doesn't she look a lot like Mama? Doesn't she look a lot like Mama? Okay, these are Mama's, like her sisters, and there's Mama's mother-in-law, okay? And all of them are calcium ions working to control the poor bastard, okay? The poor bastard potassium who just tries to, make sure everything functions, all right? So what I'm trying to say is Mama comes home, she gets on the phone, she calls up her sister, she calls up her mother-in-law, calls up other sister and says, come on over, come on over. And so they come over, and then on Mama's authority, they get more power in the house than they ever should be allowed to have, and they start making things happen in a cell. So remember that. Secondary calcium release from the endoplasmic reticulum is like Mommy's mother-in-law, and additional calcium release, like when calcium moves around the signal inside the cell, usually it's going to be coming out of the endoplasmic reticulum. Think of that as being like Mommy's sisters doing more bossing around. And this other lady over here is probably Mommy's friend, and she thinks she's a boss too when she comes over. She's got all this estrogen female power in the house, and they're bossing the good, hardworking men around. Okay, so I'm just going to show you what that translates to in terms of physiology. So here's the cardiac action potential, all right? And this is just showing you the directions of the ions. Here's the cytoplasm, here's the extracellular space, also called the extracellular matrix, okay? And you'll find it very easy to learn this now that you know that calcium and sodium always begin high. So that's why you see sodium coming into the cell to massively depolarize the cell. Calcium coming into the cell maintains the plateau of depolarization, okay? And later on, you're going to get some some potassium exit that's part of this action potential. But the important thing to realize is what we're going to talk about is the secondary changes in the cell. So here's the secondary changes that you need to know that I was referring to with the escalation of the metaphor to include the mother-in-law and the sisters of Big Mama Calcium Aristocrat. The calcium coming in through the T tubules, through the voltage-gated calcium channel, L-type calcium channel, will bind to the ryan-odine receptors on the sarcoplasmic reticulum, which is really like the endoplasmic reticulum in any other cell. Muscle cells will call it sarcoplasm. Okay, and then the endoplasmic reticulum has storage. It's a reservoir of calcium. And so this calcium binding the ryan-odine, so RO is for Ryan, like the name Ryan. Odine's like Odine's curse, the sleeping curse. Okay, so ryan-odine receptors, and that'll cause release of calcium from the endoplasmic reticulum. That will then go and bind troponin for cardiac muscle contraction. So this is what is called excitation, depolarization of a cell, excitation, contraction, coupling. And it's due to secondary calcium release. So the initial part of the action potential was related to the primary entry of calcium for maintaining the plateau phase of the action potential. That's what this orange line is for. The blue line symbolizes potassium in these diagrams. The red line symbolizes sodium, okay? This is sodium coming across the gap junctions here, which gets this little initial milder slope of upward depolarization going, okay? But the key point of this slide, why am I showing it to you? To make the point that this secondary calcium release from the endoplasmic reticulum, that's like Mama Calcium's mother-in-law bossing me around. I would walk into the kitchen and my mother-in-law would just give me endless shit. She did not want me in the kitchen. If I put the sink on, why are you wasting water? If I put the light on, why are you wasting electricity? It's like no matter what you do around women, they bitch at you. If you go to do your laundry, they go, why are you setting the controls like that? You're doing it wrong. You're going to break the machine. I can tell you, I've done my laundry for decades and decades, all by myself, never had a problem. But all of a sudden, when I'm around mama or mother-in-law, I'm always doing it wrong, okay? Now, and besides, I'm the one paying all the bills, but I'm the big criminal that I wasted electricity or I wasted water in the kitchen sink, okay? So anyways, I'm just making the point that this secondary release of calcium induced by calcium itself is called CICR, for calcium-induced calcium release, okay? And then you're going to have a pump, because now after the skeletal muscle or the cardiac muscle in this case is contracted, it needs to turn itself off to relax. So it has to pump calcium back into the endoplasmic reticulum, or the sarcoplasmic reticulum as it is called. So it's going to use something called the SERCA pump. SERCA pump is S-E-R-C-A, and that means sarcoplasm endoplasmic reticulum calcium ATP pump, or ATPase. So this ATP is going to be cleaved, and the energy from releasing that phosphate is going to be used to generate energy to pump calcium into the cell. It binds to this calsequestrin binding protein in the sarcoplasmic reticulum. Okay, but that's how it works. So that's how the cell turns its on and converts the initial calcium entry into contraction. Okay, and other cells are going to do something similar. To pump the calcium out of the cell, it'll pump very rapidly through the NCX, the knockout exchanger. There's another pump that's not as fast, but all cells have it. It's a PMCA, that's plasma membrane calcium ATPase, okay? And that's a way to also pump calcium out of the cell. One little detail, I'm not going to go into a lot of detail about it, but just to let you know, you have an autonomic nervous system, and there's SANS and PANS. SANS is like the accelerator if you're driving a car. You hit the accelerator and speed up. PANS is like the brake to slow things down. Okay, so what that means is by coupling through a G protein, when the sympathetic autonomic nervous system hormones, that's stress, fight or flight, adrenaline, noradrenaline, same thing as epinephrine, norepinephrine, bind to the receptor, the beta receptor, they will activate the positive stimulatory G protein, which then activates through these secondary mechanisms to stimulate increased calcium entry into the cell. Okay? So that's a secondary, that's how your stress system ramps up cardiac activity. And it ramps up activity in other things that are needed to respond to stress, like your skeletal muscles will also respond to stress. PANS will bind to a muscarinic receptor, and it will block the activation of cyclic AMP. So it'll decrease calcium. So that decreases cardiac contractility and decreases heart rate. Okay, but just so you know, that's how your body turns things on and off. So SANS is fight or flight. PANS is rest and digest, feed and breed. Okay, but that's how it's done. Now, here's just a slide from an article about the role of mitochondria in cardiac contraction. So again, you see the T-tubule, you see the L-type calcium channel, calcium enters, it binds to the sarcoplasmic reticulum, causes calcium-induced calcium release, the calcium goes into the cytoplasm, it then enters the mitochondria through what is called the VDAC channel, the voltage-dependent anion channel, okay? And it'll then go through and that's for the outer mitochondrial membrane. Through the inner mitochondrial membrane, it'll go through the MCU, mitochondrial calcium uniporter, and it enters the mitochondria. Okay, the main point I showed you this slide is just so you know, calcium entry into the mitochondria causes activation of the tricarboxylic acid cycle, which is Krebs cycle. All right, it activates pyruvate dehydrogenase, and this activation will get the mitochondria to run more quickly, to more quickly produce ATP. So again, this was the idea of the secondary calcium release, like, the wife's, the mother-in-law and the wife's sisters bossing things around, having this effect. That's the effect of secondary calcium release. Okay, so it also was coupled. It goes down here also to bind to troponin to couple excitation to contraction, but it also is coupled towards increasing ATP production in the mitochondria. Okay, and that's in a cardiac muscle cell. All right. Now going back to the cell, like I talked about, you'll get glutamate is the neurotransmitter, and that will travel, merge with the plasma membrane, travel across the synaptic cleft. This is a brain synapse. Activate AMPA, let sodium in, depolarize the cell, magnesium bounces out, now calcium can come in through the NMDA receptor. Okay, we're going to talk a little bit about neurophysiology now, just giving you the overview. So this was the AMPA channel, sodium channel. This was the NMDA channel, a calcium channel. Okay, there's coincident detectors. For example, glutamate binds to the NMDA receptor. Glycine also binds to the NMDA receptor. Okay, but these are ionotropic receptors, meaning that they're ion channels, but this M right here next to glutamate, so this is a glutamate receptor also, but this is metabotropic, so think of these as being metabolic glutamate receptors, and they are attached to a series of proteins that carry out additional effects. So when it binds to the metabotropic glutamate receptor, this will work again through a coupling of a G protein, and it's going to work through a phospholipase C, and it's going to cleave a plasma membrane phospholipid, and it's going to release something called IP3. Okay? Nothing to do with the joke about the person in the pool whose name is IP Freely. Okay, so IP3, once it's cleaved from the phospholipid of the inner leaflet of the plasma membrane, it will travel to the endoplasmic reticulum of the neuron, and it will bind to the IP3 receptor, and it will cause the release of more calcium, and that will have secondary effects. So again, this first calcium coming in, that's Big Mama, the aristocrat ion, okay? And the secondary released calcium is like Big Mama, once she comes home, she invites her mother-in-law, to boss you around, and her sisters to boss you around even more, okay? So that's how neurons will also they can use this as an amplification mechanism, okay? So you don't need to let that much calcium in through the cytoplasm. You can manage it with some locally released additional calcium from the endoplasmic reticulum, okay? And then when it's time to relax and turn itself off, this calcium has to be pumped out. Again, the knock exchanger cranking away can pump out 2,000 calcium per second. The plasma membrane calcium ATP pump uses an ATP, and it's much slower, but it's high affinity. Then the circuit pump also uses an ATP to pump calcium into the endoplasmic reticulum. Okay, because normally the calcium level in the cytoplasm is infinitesimal. It's next to nothing. That's a nanomolar quantity. It's literally 15,000 times higher in the extracellular space than it is intracellular. Okay, there's only one mama. There's only one mama, the big boss, and everybody knows who she is. Okay, now there's a lot of things that will contribute to increasing cytoplasmic calcium concentration. I'm just going to show you a few of them. Aspartame, the artificial sweetener, that will cause activation of the NMDA receptor. Monosodium glutamate, manufactured free glutamate in processed food to make it taste better. The glutamate gets released from that, and then you have an excess of glutamate in the body. That will also excite the NMDA receptor. So those are called excitotoxins. Okay. Glycine phosphate, which is glyphosate, the processed food stuff that's sprayed as a herbicide on the non-organic soy and a lot of other foods, that also is an excitotoxin. It is bad for your brain. Okay, if you have a mitochondrial inhibitor, that has the equivalent effect because you'll be not able to make as much ATP, so you won't be able to pump calcium out of the cell cytoplasm as quickly, and it will accumulate in the cytoplasm. Also, if you have a SERCA inhibitor, once again, you can't pump calcium out of the cytoplasm, so you will have calcium accumulating in the cytoplasm. All right? So I'm just teaching you how it all works. That's how the thinking process goes for figuring out neurophysiology. An additional thing in neurophysiology, if you have psychological stress, cortisol will also cause the stimulation of more glutamate release. Okay, cell phones will cause activation of voltage-gated calcium channels, so you don't want to hold your cell phone next to your head. Always use a speakerphone unless it's some special, important, private matter. But otherwise, you want to use the speakerphone, because holding it right next to your head, you'll get more calcium passing through the voltage-gated. VGCC is voltage-gated calcium channel. Okay. Also, when a cell goes into fight or flight mode, activation, because all of a sudden, you're walking through a forest, and the purpose of the brain is you can walk through a forest, a prairie, or a jungle and survive and eventually reproduce. Okay, so your brain's always asking itself, things are cool or they're not cool. Things are cool, things are not cool. Things are cool, you can just walk along, do whatever you want to do, go over to the fruit tree and pick some fruit, get something to eat. Okay, things are not cool. There's 3 coyotes walking towards you. Okay, you got to be ready to run or to climb a tree or do something. Okay, so you're going to need a lot more intense activity. So when this neuron has to ramp itself up, you've got contact sites between the mitochondrial membrane, the mitochondria, and the endoplasmic reticulum. These are called MAMs, mitochondrial associated membranes. And the endoplasmic reticulum will send its calcium there. Okay, there's things in this contact site. We're not going to talk about all the different receptors and whatnot. But I'm just making the point that this idea of secondary calcium metabolism is relevant. The plasma membrane is far more relevant, but the most important thing to get out of this lecture was how God created the earth with the extracellular space being salt water. So it's high in sodium and high in calcium because the water rinses over the rock, the limestone. If you remember that, you'll be in good shape the rest of your career for understanding membrane physiology, action potentials, EKGs, and all this stuff. Okay, and then you got to know the personality of the ions. Calcium is big mama, boss, matriarch, bosses everybody around. She's not reasonable. What she says goes. There is no discussion. There is no argument. You do what mama says. Okay. Then number 2 is to remember that potassium is a good guy. Potassium's like dear old dad, working his ass off so the family has bread on the table and a roof over their head and nobody appreciates him. Okay, that's potassium. And then magnesium is the big hero. Magnesium's the hero who hangs on to ATP and prevents it from bursting apart prematurely. Okay, so he makes the difficult reactions. He's like the guy working in the steel mill, making sure that stuff works. He's like the guy working out on the oil rig, a strong, tough guy. Okay, he's also a guard. He's got a second job working as a security guard where he guards the NMDA channel and does not let calcium come through there when it's not supposed to. Okay, and then you've got the angry poor. There's always the angry poor everywhere, and the angry poor is trying to bust into the city. You do not let them come in unless you need them for cheap manual labor. Okay, and then you're going to pay them as little as possible. Okay, so anyways, that's the angry poor. That is your sodium. And then we talked also about secondary release of calcium from inside the cell, from the endoplasmic reticulum. And that's like when Big Mama comes home, she gets on the phone, she calls up her mother, your mother-in-law, to come over and boss you around, and she calls up her sisters to come over and boss you around even more. Okay, and that's how a cell works. Hope that was helpful.